Hi everyone, welcome to this OsmoDevCall. Today I will be explaining everything you need to know to use the iceE1usb, more specifically how to use it with the Osmocom's TNI software stack. But first, for those that don't already know, what is the iceE1usb? Well, this is it. As the name indicates, it's a USB peripheral that allows interfacing to E1 lines, and it's based around the ice40 FPGA. It is fully open source, hardware design, schematic, PCB, case mechanical design, FPGA gateway, associated RISC-V firmware, and the entire host computer driver stack. You can find all the sources related to the device itself in the Osmo E1 hardware Osmocom Git repository. The host software side is spread around a bit, but we'll dig into that later. All the details about the project can be found on the project wiki page on the Osmocom wiki. If you're watching the recording of this talk, you should definitely check it out since some of the information contained here might be outdated by the time you watch it, especially regarding not implemented function or the exact meaning of the LED indicators or details like that. Here I will not be focusing on the internals of the iceE1usb. For that you can refer to previous OsmoDevCon recordings. More specifically, in 2018, Harald introduced the whole idea of a software-defined E1 interface, and in 2019 I presented the work in progress on the ice40 implementation of that concept. And what's presented there is pretty much what ended up in the production hardware. You can find the links to both the recordings of the presentation and the associated slides on the project page. Okay, let's get started by getting more familiar with the device itself. On one side, you find the two E1 interfaces using the classic E1 pinout, same as the Dfu cards for instance. Some internal jumper blocks can be changed to swap RX stakes to support NTT roles if you're using straight cables for instance. But I'd only use that if really necessary, because opening the device, or rather closing it, can be a bit of a pain, especially aligning the light pipe with its matching hole in the front panel. Trust me, after assembling the whole first batch, I'd definitely recommend against it. A small note about the E1 interface is that we don't use a real E1 LIU or line interface unit, and so we only officially support short-haul E1, which is fine for lab use or production use where the BTS is nearby for instance, but I wouldn't recommend trying to use it with multi-kilometers E1 links. The hardware and FPGA gateway are fully ready for dual port operation, but the firmware and software stack are currently limited to using port 0 only. There has been some preliminary work done, but it hasn't been a priority thus far. The LEDs on the top of each port indicate the link status, although current firmware support for this is rather limited, and the only two states are blinking green, indicating it's looking for an E1 signal, trying to align, and solid green means that a valid E1 lock has been acquired. In the future, more link status reporting like no signal or CSC error, remote alarm and stuff like that could be reporting using the off state and the other amber color LED. Again, Wikidoc will be updated once this is implemented. On this side of the device, you can also see a tiny hole where you can insert a paper clip or such to press the push button inside. This is used to enter recovery mode, but more on that later. Moving on to the other side of the device, first obvious thing is the Usbc port in the center, not much to say about that. It's a USB 2.0 full-speed device, and we try our best to meet the USB specs. I think the only thing we don't really support is suspend mode, where we should technically drop power usage to very low levels, and we just don't. Above the USB is a general-purpose RGB LED that indicates the global device state. A fast blue blink indicates the device is in bootloader mode. Green and red colors are used for runtime mode, with green being OK, and red indicating some kind of issue. The blinking is used to indicate active data transfer to the host. Although currently the blinking does start when the host software starts, it doesn't actually stop once the host software disconnects. So yeah, firmware is a work in progress. On the left hand side, there is the 2.5mm TRS jack that's used for classic Osmocom CMOS 3V 3-level UART. This is used for a debug console and should only be needed by developer working on the firmware. And after that, the SMA connector, which is used for the internal GPS module. It's meant for the usual active GPS L1 antenna, providing 3.3V DC bias up to 40 mA. The module used should support classic GPS, Galileo, and Baidu. GPS function support is currently not implemented in the firmware, but it's meant for locking the internal VCXO to a precise timing reference, and also to provide GPS NMEA messages to the host for whatever the host wants to do with them. And finally, the RG45 connector on this side is reserved for future extension and isn't actually connected to anything yet. There are internal headers that allow to connect small daughter cards for whatever extra hardware is needed, but currently none have been designed or implemented. Some ideas were RS422 interfaces to implement GPS module emulation for the RBS 6000 BTS, or some GPIO to control or monitor the environment, or things like that. Moving on to the actual usage part. The first thing to do if either the device is new or hasn't been used in a while is to upgrade the gateway and firmware to the latest version. Brand new devices will probably still have the factory test firmware loaded, and although it gets recognized as a USB device, that firmware can't operate normally. This is easy to spot in either dmessage or LSUSB, since the device will show up with iceEUSB test firmware as the product string and 0xE1E1 as the product ID. The E1 amber LEDs might also be blinking. The iceE1usb uses the standard USB Dfu class mechanism for firmware update. It exposes two alternate settings, one to upgrade the FPGA gateway, the other for the RISC-V firmware. To upgrade, the first step is to enter bootloader mode. Although not strictly necessary, because if all goes well, the FUTIL can do the switch on its own, I prefer to do it manually as a sanity check. If the device has a working firmware, that includes the test firmware, it should just show up when doing dfutil-l as a runtime device. In that case, to reboot to Dfu mode, all that's needed is to use dfutil-e option. Note that if there are several Dfu capable devices, narrowing down the targeted device might be needed. A good way to do that is to use the -S option and to specify the serial number as shown in the device list obtained above. Once in Dfu mode, the LED above the USB connector should be fast blinking blue. If the device didn't show up, something must be wrong. If the device is enumerating in dmessage and or LSUSB, but it doesn't show up in dfutil and an error about cannot open Dfu device shows up, then it's worth checking permission to make sure your user can access USB devices. For instance, on this Ubuntu install, I created a udev rule giving access to all possible VID PID of the iceE1usb to the plugdev group, then ran udev admin trigger to force a refresh. Once the permissions are fixed, the device should be listed by dfutil. If on the other hand the device never showed up in dfutil and or doesn't even enumerate in dmessage or LSUSB, then the loaded firmware might be corrupted and using emergency recovery mode is the next thing to try. To do so, unplug the USB from the iceE1usb, use a paperclip to press on the button inside the tiny hole on the lower left side next to the E1 connector, and while holding it pressed, plug the USB connector. At that point, the LED should be solid red, and once the button is released, it will switch to fast blinking blue, indicating that Dfu bootloader is running. Once the iceE1usb is in bootloader mode, dfutil will list both available alternate settings with their respective ID and description. At this point, you can download the latest binary release for the gateway and firmware, or build them yourself from sources if you like. The links for both can be found on the project wiki page. Once that's done, all that's left to do is to use dfutil to flash both files to the respective section. Make sure to use the right file for the right section, or recovery mode will be needed to try again. Also, unless you know for sure there are no compatibility issues, both the gateway and the matching firmware should be flashed together at the same time, since different versions of gateway firmware might not be compatible with each other and might result in either the device not working at all or some weird behavior. After the flashing, the device needs to be reset, either by unplugging, replugging, or using dfutil again to send a detach command that will trigger the reset. The front side LED should go back to either red or green depending if an E1 link is already connected or not. Now that we have an up-to-date device and it's properly recognized by the OS, we can get started with the host software stack. There are two options here. The first one is to use the Osmo E1d daemon. This is a user space daemon that will use libusb to communicate with the iceE1usb and allow sharing it with both the Osmo BSC and Osmo MGW or any other application if need be. This intermediate process is needed because E1 will carry both the control plane handled by Osmo BSC and the data voice plane handled by Osmo MGW, but only one process at a time can really talk to a USB interface. So the easiest option we found was to have a daemon coordinate the access, and it communicates with Unix socket and pipe descriptors to any local process that needs E1 access. Once downloaded and built using the classic autoreconf configure make install cycle, the Osmo E1d process can be started. There is a configuration file where you can configure logging, for instance, or virtual devices, but for the moment it's fine to just use an empty one. If we try to start the Osmo E1d process right now, we would see an error about failing to set real-time priority. This is because the process tries to elevate its scheduling priority, which is needed for reliable communication. E1 is synchronous, so it's important that we keep up, and we can't introduce too much buffering either, since this would directly translate into latency. To allow the process to set its own priority, we can use capabilities on the binaries using setcap. And now we can start Osmo E1d, and it's not reporting that error anymore. You can see here a message about the alignment being lost. That's because currently nothing is plugged into the E1 port. The LED on the front also started slowly blinking red to indicate that there is active data transfer with the host. Now we can plug in a BTS. In this case, it's a Nokia Insight. And we can see Osmo E1d properly sees the link going up and gaining E1 alignment. The RGB LED goes green, and the link indicator above the E1 goes solid green as well. With Osmo E1d running and the BTS connected, we need to configure Osmo BSC and Osmo MGW. I won't go into all the details on how to configure the whole Osmocom CNI stack. This would be way beyond the scope of this talk. So I will only focus on what's specific to using the iceE1usb instead of a classic E1 card using DADI or MESDN. But before we can configure either of Osmo BSC or Osmo MGW, we actually need to add E1d support for them. Both of them use the libosmo abis library to abstract the low-level line access, so we only need to rebuild that with E1d support. With Osmo E1d now installed, the libosmo E1d shade library is available, and so we can just reconfigure libosmo abis with the enable E1d option, rebuild and install it, and Osmo BSC and Osmo MGW will gain support for E1d. Once that's done, the configuration file for the BSC needs a tiny bit of editing. The previous configuration was the example configuration for Nokia Insight using DADI, and the only thing that needs changing is replacing DADI with E1d as the driver in the E1 input section. And then the exact same change for the MGW config. Although here, I won't bother starting the MGW since I only have one test phone and can't establish voice calls anyway. I already have the rest of the Osmocom CNI stack running, so the only thing left to do is start the BSC. Osmo E1d throws some error. This is actually normal. As part of the init process, the BSC will command the BTS to reset, which drops the E1 link for a moment, and that's what gets reported. But the links comes back up very soon after that, and we can see BSC showing the successful bootstrap of the OML link and the RSL link, so the network is now up and running. There's also an alarm raised by the BTS because its internal clock is not in sync with the E1 link, not a problem here for a quick lab test. So now we can attach a phone and send an SMS to it to confirm that everything is working. So there you go, that was pretty simple, right? Really not much changes from a normal E1 setup. As I mentioned earlier, Osmo E1d is only one of the two available options. The other one is an experimental kernel driver written by Harald that makes the iceE1usb show up as a classic DADI device. You can see the status in ticket 4923 on the Osmocom Redmine tracker, and the code is up on GitHub. In this case, the kernel is the one that's multiplexing access to the USB device, and the application have no idea. The advantage of this solution is that it works out of the box with any DADI compatible application without needing any modification. So non-Osmocom application like Asterisk, FreeSwitch, etc. should run just fine, although I'm not sure if anyone tested that yet. That also includes the kernel itself, and so you can use the generic HDLC layer in Linux to run FreeRelay, PPP, X25, all of that over E1. The downside, of course, is that a custom DADI Linux kernel driver needs to be built and installed on the system. On my Ubuntu install, I also had to install the DADI tools manually since you can't install the tools package without installing the driver package. With the driver installed, and Osmo E1d stopped of course, you can just mod probe iceE1usb.ko and it will recognize the USB device. The unsupported interface message in the log is normal, it's just the driver indicating one of the USB interface isn't handled, but it's the DFU interface and that's expected. Just like any other DADI device, it needs to be configured by DADI CFG utility. I have here a very minimal system.conf to do so. Proper configuration is confirmed in dmessage, and the fact that the RGB LED on the device starts its slow blink indicating that the traffic is flowing between the iceE1usb and the host. All that remains is to change back the Osmo BSC and Osmo MGW configuration to use DADI and start the Osmo BSC process again. And same as with the Osmo E1d, we can see in the dmessage some normal transient error when the BTS is restarted. But the links eventually recovers, and Osmo BSC bootstraps OML and RSL links, and the network comes up. Okay, that concludes my small demonstration of the iceE1usb. If you want one, they are available from the Sysmocom shop, and if you're an open source developer or hobbyist, feel free to contact Sysmocom for available discounts. Being fully open source, you're of course welcome to build your own. Thanks you all for watching, and we can now move on to the Q&A section. Okay, so does anyone have any questions?
Hi, Sylvain. The DFU bootloader, I mean, this is just a technicality, not really related to E1. The FPGA bootloader, is this still running then on the RISC-V, or is this there is a CPU-less DFU bootloader,
No,
I think, for the ice40?
It's running on a different RISC-V. So the way this works is that the FPGA has the ability to reconfigure itself from a different address in Flash. And so when you first plug the device, what happens is that it starts a first FPGA bit stream, which There's very little. The only thing it does is it looks if the button, the emergency recovery button, is pressed or not. If it is pressed, it will reconfigure itself with bitstream number, that was bitstream number 0. It will reconfigure itself with bitstream number 1, which is the DFU bootloader, which includes a RISC-V firmware and a FPGA bitstream. And if the button is not pressed, it will go to bitstream number 2, which is the main application firmware that we usually flash and that you can update. The two first bitstream, which form the bootloader together, along with the RISC-V firmware for the DFU bootloader, are stored at the very beginning of Flash, and that section of Flash is locked to prevent accidental overwrite.
Okay, thanks. Then let me just ask a second question. How difficult do you think will it be to support the second E1? Is this kind of only doing the work, or is there really some heavy optimization necessary, for example, because you are already at the limit of the fabric on the FPGA?
No, so as I mentioned it quickly, but the gateware is actually completed. So the entire FPGA bitstream itself supports both E1. So it's really just the RISC-V code that needs to add support for the second E1 link, but the actual there's nothing to change in the FPGA basically. And a good part of the work has actually already been done. I have something somewhere in a branch. But since me and Harald were kind of working on the firmware at the same time, well, that branch actually conflicts all over the place now. And so I need to solve all the merge conflicts that were created. But yeah, the descriptors, we know that the only kind of small complication there was that by default I was allocating. So the communication to the host is done via USB isochronous endpoints, and the way the both ports are exposed is that they're exposed as distinct interfaces, basically. And when you describe the bandwidth that allocated to one port, I just allocated too much bandwidth, that kind of a safety to recover from overflow condition more quickly. The problem is that if you take that bandwidth, you multiply it by 2 for 2 ports, that will be more bandwidth than the entire USB bus has. And so obviously the host was kind of complaining. So I had to dial that back a little, but that's not really a problem in the end. Like at the moment, there hasn't been like a huge pressure to support 2 ports anyway. Mostly what I'd like to do also for that device is port the E1, like the passive listening device.
E1 tracer.
The E1 tracer, exactly. So that that firmware is actually usable on that device, and also possibly supporting a mode where you don't need the external tap, but the bits are just kind of relayed internally. It's not entirely passive then, but that means that you don't need any external hardware. You can just plug one device on one side and the other on the other side.
E1 man in the middle.
Yeah, exactly.
Just like SimTrace all over again. Too many modes and only one is supported in the firmware.
Right, exactly. I mean, the hardware part is the easy part. It's always the firmware that.
Does anyone here have any E1 use cases outside of Osmocom? Just curious if there are any people on this call who have a use case or who want to do something with it that is not GSM related.
I still occasionally see like ISDN out in the field for voice lines and carrying SS7, etc. I could see a use for it there.
Sure, theoretically, of course, yes. I know. I was just wondering whether there's anyone who has any context. So Martin Hauke brings up that yes, you can use Dati with net HTLC and Linux, generic HTLC, so you can play frame relay on Linux. Yes, that's correct, and it's actually we implemented this at Sysmocom some time ago using an OsmoGB proxy and the entire libosmogb code. Supports GB interface over frame relay exactly using this route. So that is, yes, of course, you can use IP over frame relay, but you can also speak GB interface over frame relay if you want to talk to some really ancient BSC or ancient PCU or SGSN.
Thanks everyone again, and see you at the next OsmoDevCall.